What if I told you that every connection we've ever felt, every bond, every interaction, every moment of seeming coincidence, might trace its roots back to a single, unfathomable event at the dawn of time? The universe's first quantum entanglement wasn't just a flicker in the void. It was the spark that set reality itself into motion, weaving an invisible web that ties everything together in ways we're only beginning to glimpse. Picture this: two particles born light years apart, dancing in perfect sync without ever touching. Change one, and the other responds instantly, as if space and time don't exist between them. This isn't science fiction, it's the mind-bending reality of quantum entanglement, a phenomenon so strange even Einstein called it spooky action at a distance. But here's the real mystery: how did it all begin? If entanglement binds the universe, what tangled the first threads? The answer could rewrite everything we know about existence. Some scientists believe the first entanglement didn't just happen. It was the universe's way of talking to itself, a whisper that grew into the cosmos we see today. Others think it might have been a cosmic accident, a flaw in the fabric of reality that became its defining feature. And then there are the wilder ideas. What if entanglement isn't just a physical phenomenon but something deeper, a shadow of higher dimensions, or even evidence of a universe that existed before our own? That's where this journey begins. Over the next 30 theories, we'll dive into the boldest, most provocative ideas about how quantum entanglement first threaded itself into the fabric of reality. From the edges of black holes to the birth of time itself, these aren't just guesses, they're windows into the universe's best-kept secrets, so buckle up. Whether you're a science enthusiast or just someone who loves a good cosmic mystery, what you're about to hear will challenge how you see everything from the stars above to the ground beneath your feet. Because if entanglement is the universe's first language, we're finally learning how to listen. The moment the universe burst into existence, it wasn't just a fireball of energy, it was a symphony of perfect synchronization. Picture the Big Bang not as a chaotic explosion, but as a cosmic orchestra tuning up, every particle humming in unison before flying apart. This is where our first theory takes root. Entanglement didn't emerge later, it was there from the very first breath of reality. When everything in the cosmos was squeezed into a space smaller than an atom, particles weren't just neighbors, they were practically the same entity, bound by a connection so intimate that even as they raced apart across billions of light years, that bond never broke. Think of it like tearing a piece of paper in half. No matter how far you separate the two pieces, their edges still match perfectly, a hidden record of their shared origin. In the same way, particles born together in the Big Bang might still carry that invisible link, responding to each other instantly across cosmic distances. This isn't just poetic speculation. Experiments with entangled photons in labs today echo this idea, showing particles mirroring each other's states faster than light could travel between them. If that behavior scales up to the universe's birth, it could explain why galaxies on opposite sides of the sky seem weirdly coordinated, as if whispers from the Big Bang still guide them. But here's the twist: if entanglement was woven into the universe's fabric from the start, it challenges how we think about space and time. Einstein's relativity insists nothing can outpace light, yet entangled particles flout that rule effortlessly. Some physicists argue this means entanglement isn't traveling, it's revealing a deeper layer of reality where separation is an illusion, like two ends of a single string. Others go further, suggesting the Big Bang didn't just create entangled particles, it entangled space itself, stitching the cosmos into a single, living tapestry where every thread tugs on every other. The implications are staggering. If entanglement is primordial, it could solve cosmic mysteries like why the universe looks so uniform in all directions. Maybe the far-off galaxies we see aren't just similar, they're still dancing to the same tune, their motions encoded in those first quantum whispers. or perhaps entanglement seeded the structure of everything from galaxy clusters to the atoms in your hand. One thing's certain, if this theory holds, the Big Bang wasn't just a beginning, it was the universe's first conversation, and we're only now learning how to hear it. Imagine the universe in its first moments, stretching faster than the speed of light, not just expanding, but inflating like a balloon blown up in a fraction of a second. This was cosmic inflation, a burst of growth so violent it turned a speck of space into something approaching the cosmos we know, and hidden in that frenzy might lie the origins of quantum entanglement. Here's why this changes everything. When inflation stretched spacetime, it didn't just magnify distances, it could have frozen quantum connections into the fabric of reality. Picture two particles vibrating in sync, so close they're practically overlapping. Inflation yanks them apart at unimaginable speeds, but their quantum states stay locked together, like dancers pulled to opposite sides of a ballroom yet still moving in perfect harmony. This isn't just theoretical. Scientists studying the cosmic microwave background, the afterglow of the Big Bang, have spotted strange correlations between regions of space that should have never been in contact. The explanation: those areas might have been neighbors before inflation tore them apart, their entanglement preserved across billions of light years. But the real magic is in the scale. Inflation doesn't just create tiny entangled pairs, it could weave quantum links across the entire universe. Think of it as a cosmic spiderweb, with threads spun so wide they connect galaxies we see as separate today. This might solve one of cosmology's biggest puzzles: why the universe looks so uniform. If far-flung regions were once quantumly linked, their similarities aren't coincidence. They're echoes of an ancient connection, like leaves on a tree still trembling from the same gust of wind. Not everyone agrees, of course. Some argue inflation would have shredded delicate quantum states, leaving no entanglement behind. Others propose an even wilder idea, that inflation didn't just preserve entanglement but amplified it, turning quantum whispers into the blueprint for cosmic structure. After all, if gravity can bend light, why couldn't quantum links bend the very shape of spacetime? Whatever the truth, this theory forces us to rethink what distance even means. Two particles can be galaxies apart, yet as bound as if they were touching, proof that the universe's first expansion didn't just create space, but stitched it together with invisible threads we're only now beginning to trace. Deep in the seething chaos of the early universe, before stars or galaxies existed, tiny black holes may have formed not from collapsing stars, but from the raw density of space itself. These primordial black holes, some no heavier than a mountain yet denser than an atom, could hold the key to one of entanglement's strangest chapters. Because if they existed, their event horizons weren't just traps for matter, they were quantum mixing bowls, scrambling particles into entangled pairs like cosmic dice forever rolling in sync. Here's how it might work. When a particle falls toward a black hole's edge, it stretches like taffy, splitting into two versions, one swallowed by the darkness, the other radiated away as faint quantum noise. Normally, these twins are forever lost to each other, but primordial black holes born in the universe's first seconds could have forged an even deeper bond. With space so tightly packed back then, two black holes might have formed impossibly close, their gravitational whirlpools nearly touching. Anything falling into one could have entangled not just with its own escaped twin, but with particles caught in the neighboring black hole's grip. The result, a quantum bridge between 2 points in space, a secret handshake encoded in the very fabric of the cosmos. This isn't just theoretical sleight of hand. Modern telescopes hunting for gravitational waves, ripples in spacetime from black hole collisions, have detected signals that could match primordial black holes. And if those ancient relics exist, their entanglement might still echo today. Picture two black holes billions of light years apart, yet still quantumly linked, their interiors vibrating in unison like drumheads tapped by the same invisible hand. It's a spine-tingling possibility. that the universe's first black holes didn't just consume, they connected, weaving threads through space-time that might still tug on reality as we know it. The implications rewrite black hole physics as we understand it. If entanglement survived the trip across an event horizon, it challenges Stephen Hawking's famous paradox about information being lost in black holes. Maybe the data isn't destroyed, just translated, hidden in the quantum ties between particles we once thought were gone forever. Some physicists even speculate these primordial entanglements could explain dark matter, with ancient black holes acting as invisible anchors that shape galaxies through their ghostly quantum bonds. Of course, not everyone's convinced. Critics argue that the violence of the early universe would have shredded such delicate quantum links. But supporters counter with an eerie observation. If entanglement can defy space and time today, why couldn't it have endured from the moment space-time itself was new? After all, black holes aren't just cosmic vacuum cleaners, they're the universe's most extreme laboratories, where the rules we know bend and twist into something stranger. And if those rules include quantum bonds surviving the birth of reality, it means our cosmos might be far more connected, far more woven together than we ever dreamed. Even empty space isn't truly empty. If you could peer into the void with perfect vision, you'd see a seething ocean of energy particles flickering in and out of existence so fast they barely leave a trace. These quantum fluctuations, the universe's smallest tremors, might hold the secret to its first entangled connections. Imagine the vacuum of space not as stillness, but as a cosmic dance floor where particles materialize in matched pairs, spin together for a fleeting instant, then vanish back into the dark. Now stretch that moment across the birth of reality itself, and you've got a recipe for entanglement woven into the fabric of everything. This idea ties directly to one of quantum physics' strangest phenomena, virtual particles. Normally, these fleeting duos, matter and antimatter twins, annihilate each other too quickly to matter. But in the extreme conditions of the early universe, where space was smaller and energy unimaginably dense, some pairs could have been yanked apart before they had time to collide. Picture two particles ripped from each other's grasp by the universe's explosive growth, their connection stretched but never broken. It's like tearing a piece of paper so fast the fibers at the edge stay linked even as the halves fly apart. These stranded twins would carry their quantum sync into the expanding cosmos, becoming the first entangled pairs. What's even wilder is where this energy comes from. Empty space isn't passive, it crackles with zero-point energy, a baseline hum that never fades. Some theorists suggest this energy isn't just background noise, it's the engine that drove the universe's first quantum links. Think of it like a cosmic casino where space itself keeps spinning the roulette wheel, generating endless particle pairs. Most collapse instantly, but in the frenzy of the Big Bang, some winners got scooped up into the growing cosmos, their entanglement locked in place like a fossil in expanding rock. The implications rewrite how we view the vacuum. Instead of a blank slate, empty space becomes a factory for quantum connections, constantly churning out potential entanglements. This could explain why entanglement seems so fundamental. It wasn't an accident, but an inevitable product of spacetime's restless energy. Experiments with Casimir plates, which measure the faint pressure of virtual particles, hint that this quantum froth is very real. And if those fluctuations birthed entanglement in the past, they might still be weaving new threads today, hidden in the spaces between stars. Not everyone agrees, of course. Critics argue that random fluctuations would create chaos, not the delicate sync we observe. But supporters counter with a twist. What if entanglement isn't the exception but the rule? Most virtual pairs vanish unnoticed, but in a young, searing hot universe, maybe only the entangled ones survived, turning quantum accidents into cosmic foundations. Either way, this theory forces us to confront a dizzying idea, that the universe's deepest bonds might have emerged from nothing more than the void's own shivering uncertainty. a reminder that even emptiness is alive with possibility. What if the entire universe is just a projection, a cosmic hologram where everything we see, touch, and experience is actually encoded on a two-dimensional surface we can't perceive? The holographic principle, one of the most radical ideas in physics, suggests exactly that. And at the heart of this mind-bending concept lies quantum entanglement, not as a side effect, but as the very glue holding spacetime together. This theory flips our understanding of reality upside down, proposing that the universe's first entanglement wasn't an event, it was the foundation of existence itself. Think of a hologram you might see on a credit card, a 3D image etched onto a flat surface. The holographic principle argues our 3D universe works the same way, with all its depth, stars, and galaxies acting like a projection from information stored on a distant two-dimensional boundary. But here's the twist: for that illusion to hold, every particle inside the universe must be entangled with bits of data on that outer surface. It's like a cosmic puppet show where the strings aren't physical, they're quantum links stretched across dimensions. This isn't just wild speculation. Physicists studying black holes discovered something startling. The information swallowed by an event horizon isn't lost. Instead, it gets smeared across the black hole's surface like data encoded on a hard drive. Scale that up to the entire cosmos, and you get the holographic principle. A universe where entanglement stitches together the fabric of reality by binding the inside to the outside. If true, the first quantum link wasn't a chance connection. It was the universe booting up its own operating system. The implications are staggering. If spacetime emerges from entangled bits on a hidden surface, it explains why particles light years apart can sync instantly. They're not really separate, just different points on the same cosmic blueprint. Picture two actors in a play, seemingly independent, yet both following the same script. Their lines match perfectly not because they're communicating, but because they're expressions of a deeper, unified code. Critics argue the math behind this is still speculative, and we've yet to find direct evidence of a universal hologram. But supporters point to eerie clues, like the way black hole physics mirrors the equations of thermodynamics, as if reality is running on hidden rules we're only glimpsing. Some even suggest that if we could decode the universe's entanglement patterns, we might find signatures of that primordial surface where everything began. Whether the holographic principle holds all the answers or not, it forces us to confront a profound possibility: that the first quantum entanglement wasn't just a spark in the dark, it was the universe learning how to exist, weaving itself into being one thread at a time. And if that's true, we're not just observers of the cosmos, we're part of its code. String theory paints a universe far stranger than the one we see, a cosmos not of solitary particles, but of tiny, vibrating strings, each humming its own unique note to build the symphony of reality. And hidden within those vibrations might be the answer to entanglement's greatest riddle. If particles aren't just points but loops of energy wriggling through higher dimensions, their quantum connections could be more than spooky action. They might be the universe's original network, threads tying everything together in ways our 3D minds struggle to grasp. Picture this: two electrons light years apart aren't separate at all. Instead, they're like buoys bobbing on an invisible ocean, their motions synced because they're tethered to the same submerged string. In string theory's framework, what we call entanglement could be literal particles linked by strands stretching through dimensions we can't perceive. These aren't ordinary threads, though. They vibrate at frequencies that determine whether a particle becomes matter, light, or even gravity itself. And if those strings tangled during the universe's birth, their knots might still bind the cosmos today, weaving quantum sync into the fabric of spacetime. This idea flips conventional physics on its head. Normally, gravity and quantum mechanics refuse to play nice. One rules the cosmos, the other the subatomic world. But if entanglement arises from strings, it could bridge that divide. Think of it like a spiderweb where each silk strand carries both tension and information. Pluck one thread and the whole web trembles. Similarly, entangled strings might transmit not just quantum states but the very force of gravity, offering a blueprint for the long-sought theory of quantum gravity. Evidence is still indirect but tantalizing. Certain black hole models in string theory suggest their interiors are vast tangles of strings with entanglement entropy, a measure of quantum connections matching their surface area. This eerie parallel hints that what we call space might emerge from stringy links, like a 3D image rising from a flat circuit board. Even the Big Bang could get a rewrite instead of a singularity. Imagine a universe-sized string network snapping taut, its vibrations birthing particles already in perfect sync. Critics argue string theory remains untested, its extra dimensions purely mathematical. Yet supporters point to recent lab experiments where holographic principles, a cousin to string theory, have successfully predicted quantum entanglement patterns. If strings are real, their hidden connections might explain why particles separated by cosmic distances still act as one. They've been dancing to the same tune all along, bound by vibrations older than time. Whether this theory holds or not, it forces us to consider a profound truth that entanglement might not be the exception in our universe, but the rule written in the loops of reality's deepest layer. What if our universe isn't alone just one thread in a vast, shimmering tapestry of parallel realities? The multiverse entanglement hypothesis takes quantum weirdness to a breathtaking scale, suggesting the first entanglement didn't happen within our cosmos, but between universes themselves. Imagine two bubbles floating in an endless foam, their surfaces brushing just long enough to share a fleeting quantum link before drifting apart. That momentary touch, some theorists argue, could have imprinted sync across realities, tying them together in ways that echo to this day. This idea isn't just cosmic poetry, it could solve one of quantum mechanics' oldest puzzles, the measurement problem. In our universe, particles exist in blurry superpositions until observed when they choose a definite state. But what triggers that choice? The multiverse answer is startling. Every possible outcome happens, just in different branches of reality. When you measure an electron spin, the universe splits, one where it's up, another where it's down. Entanglement between these branches could explain why particles seem to know each other's states instantly, because they're still whispering across the multiverse, their choices forever intertwined at birth. Think of it like a cosmic game of telephone where universes borrow cues from their neighbors. If two particles here are entangled, it might not be because they're linked directly, but because their twins in another universe are pulling the strings, their quantum states mirroring ours through hidden channels. This could explain spooky action at a distance without breaking light speed limits. The connection isn't crossing space, it's hopping realities. Experiments with quantum interference already hint at particles sensing paths they didn't take, as if they're glimpsing alternate versions of themselves. Could those ghosts be echoes of entangled multiverses? Critics argue this stretches Occam's razor to the breaking point. Why invent infinite universes to explain one? But supporters fire back with a counter-question. Why assume our universe is the only one playing the quantum game? After all, inflation theory suggests our cosmos is just one bubble in an eternally frothing multiverse. If those bubbles ever touched, even briefly, entanglement might have spilled over like paint between wet canvases, staining every reality with the same quantum patterns. The implications rewrite the meaning of randomness. What we call chance might just be the tremor of decisions made in other worlds, their quantum ripples lapping against our shores. And if entanglement truly binds the multiverse, it means our universe's first connection wasn't a solo act, but a handshake across existence itself, a reminder that even alone, we might still be part of something infinitely larger. Dark matter, the universe's invisible scaffolding, the ghostly hand shaping galaxies yet refusing to show itself, might hold the oldest secret of all. What if the first quantum entanglement didn't belong to the particles we know, but to the shadowy ones we've never seen? This theory flips the script entirely, suggesting dark matter didn't just watch the universe's birth, it orchestrated it, weaving quantum connections so vast they bent the cosmos into shape. Picture the early universe not as a storm of light and matter, but as a swirling sea of dark particles, cold and silent. Unlike ordinary particles, these wouldn't have been blasted apart by the Big Bang's fireball. Instead, they'd have drifted slowly, their gravity gently pulling them together. But what if they were also bound by something stranger? If dark matter particles entangled in those first moments, their quantum links could have acted like cosmic blueprints, guiding where galaxies would later form. Think of it like invisible ink on a map. The glowing stars and gas we see today might just be tracing patterns drawn by quantum handshakes we can't detect. The evidence is tantalizingly indirect. When astronomers map the universe's large-scale structure, they find galaxies strung along filaments like beads on a necklace with vast voids between. Computer simulations struggle to replicate this delicate web unless dark matter has some intrinsic stickiness, not just gravity, but something that makes it clump in precise ways. Quantum entanglement fits eerily well. If dark matter particles shared quantum states early on, they'd have moved in sync, their collective dance imprinting order onto the chaos. It's as if the universe's hidden skeleton was also its first quantum network, a silent conductor guiding the visible symphony. Testing this idea is devilishly hard, though. Dark matter doesn't just hide from telescopes, it barely interacts with anything, making its quantum properties nearly impossible to probe. But physicists have clever workarounds. Some hunt for faint distortions in the cosmic microwave background, the afterglow of the Big Bang, which might bear scars from dark matter's early entanglement. Others simulate exotic particles called actions, which could form quantum-linked clouds stretching across galaxies. And then there's the boldest idea of all, that dark matter entanglement might subtly warp spacetime itself, leaving gravitational ripples we could one day measure with observatories like LISA. Of course, skeptics argue this is a solution in search of a problem. Why invoke quantum spookiness when gravity alone might suffice? But proponents counter with a cosmic coincidence. The scales of quantum physics and dark matter's influence align suspiciously well. If entanglement can bridge particles across a lab today, why couldn't it have scaled up to galactic proportions when the universe was smaller than a marble? The stakes are cosmic. If dark matter truly carried the first quantum links, it means the universe's visible beauty, spiral galaxies, glittering star clusters, is just the echo of a deeper, hidden conversation. Every time we map the night sky, we might not just be tracing gravity's handiwork, but reading the faintest fingerprints of quantum bonds older than light itself. Could the universe's first quantum entanglement be older than time itself? Some theorists dare to suggest that the spooky links binding particles today might be cosmic fossils, echoes of a universe that existed before our own. This isn't just about what happened after the Big Bang, but what might have come before it, a realm where the rules of physics as we know them didn't apply yet. Imagine not a fiery beginning, but an endless cycle of universes rising and falling like tides, each collapse seeding the next explosion. And in that transition, quantum threads stretching across the abyss, refusing to snap. The math behind this is as beautiful as it is bold. If our universe emerged from the death of a previous one, a big bounce rather than a big bang, the extreme compression of that collapse could have forged quantum connections so robust they survived the rebirth of reality. Picture a universe contracting to a single, searing point, its particles squeezed so tightly their states became eternally linked. Then bang, the rebound, space exploding outward again, but those quantum handshakes still intact, woven into the fabric of the new cosmos like scars on rewritten skin. Evidence is thin but tantalizing. Certain patterns in the cosmic microwave background, the universe's oldest light, show odd irregularities that don't fit standard Big Bang models. Could these be imprints of pre-Big Bang structures, quantum knots that refuse to unravel? Even more provocative, some versions of string theory suggest black holes in a dying universe might have funneled information into the next, not as data, but as entangled states, a cosmic inheritance passed between realities. Critics argue this veers into metaphysics, with no way to test a before when time as we know it began at the Big Bang. Yet supporters counter that quantum entanglement itself defies classical notions of cause and effect. If particles can sink faster than light, why couldn't their bonds transcend the birth of spacetime? After all, the equations describing entanglement don't care about when, only how. The implications are dizzying. If true, our universe's strangest phenomenon might not be a product of its birth, but a relic of something far older, a whisper from a world we'll never see, yet still somehow touch. It's a humbling thought. Every quantum link in your body, in the stars, in the void between galaxies, might be the last frayed thread of a cosmos long gone, clinging to existence by the sheer stubbornness of its own mystery. Einstein once dismissed the idea of quantum entanglement as spooky action at a distance. But what if that spookiness wasn't magic, just physics we hadn't cracked yet? Enter wormholes, those infamous cosmic shortcuts predicted by general relativity. Far from just sci-fi plot devices, these tunnels through spacetime might hold the key to entanglement's first moments. Imagine two black holes born light years apart, their intense gravity warping space so severely that their cores stitch together, forming a bridge, an Einstein-Rosen bridge, where particles could slip between points without crossing the distance. Now shrink that idea down to quantum scales, microscopic wormholes threading through the newborn universe like invisible stitching, allowing particles to share states instantly because for a fleeting moment they weren't separate at all. Recent breakthroughs make this wild idea shockingly plausible. Physicists studying ER equals EPR, a radical hypothesis linking wormholes to entanglement EPR, have shown mathematically that entangled particles could be connected by quantum-scale wormholes too tiny to see. Picture two electrons dancing in sync, not because they're communicating faster than light, but because a submicroscopic tunnel binds them, making their separation an illusion. This isn't just theory. Lab experiments with quantum computers have simulated wormhole dynamics, observing how information hops between particles in ways that mirror traversable bridges in spacetime. The implication, entanglement might not defy Einstein's laws, it could be obeying them on scales we're only beginning to glimpse. The most tantalizing clue comes from black hole physics. When matter falls into a black hole, its information isn't lost. It's scrambled onto the event horizon like cosmic graffiti. But how wormholes might ferry that data to distant points via quantum entanglement, acting as spacetime's hidden plumbing. Apply this to the early universe, and you get a universe where every Big Bang particle was briefly connected by a web of microscopic wormholes. Their quantum states synced before the tunnels pinched shut, leaving only the spooky links we observe today. Yet skeptics raise valid questions. If wormholes enabled entanglement, why don't we detect their gravitational fingerprints? Supporters counter that quantum wormholes would be vanishingly small, evaporating almost instantly, their traces hidden in the noise of the quantum vacuum. Others propose an even wilder twist, that wormholes didn't just facilitate entanglement but emerged from it, spacetime itself knitting together to accommodate particles that refused to be apart. Whether this theory holds or not, it reshapes how we view the universe's first connections. Entanglement might not be a bizarre exception, but the natural consequence of spacetime's architecture, a reminder that the fabric of reality is far more malleable, far more threaded with hidden passageways than we ever dreamed. And if quantum wormholes truly underpin the cosmos' first bonds, it means the universe didn't just expand, it tunneled its way into existence, one entangled stitch at a time. What if entanglement isn't just a quirk of quantum physics, but the universe's original programming language, a cosmic code written into the fabric of reality at the dawn of time. This theory takes the mystery of quantum connections and flips it into something even more profound: entanglement as the operating system of existence itself, a set of primordial instructions that told spacetime how to stitch itself together. Think of the Big Bang not as a chaotic explosion, but as the first boot-up sequence, with quantum links acting like lines of code executing the universe's most basic commands. Digital physics, a radical branch of theoretical research, suggests reality might literally be computational, a vast, self-running algorithm where particles and forces are just data points in a cosmic simulation. If that's true, entanglement could be the glue holding the code together, the equivalent of a programming function that instantly syncs variables across distant parts of the system. Picture two bits of information in a computer game. Change one, and the other updates automatically because they're linked by the same underlying logic. That's precisely how entangled particles behave, responding faster than light could travel between them, as if they're not separate objects at all, but two expressions of the same line in reality's source code. The eerie parallels don't stop there. In error-correcting codes, the digital protocols that keep your phone calls clear and your Wi-Fi stable information is often distributed across multiple nodes so that if one fails, the data can be reconstructed from the others. Some physicists argue the universe does the same thing, with entanglement acting as its error correction system. When particles sync their states instantaneously, they might be reinforcing the integrity of spacetime itself, ensuring the cosmic program doesn't crash. This could explain why entanglement seems so fundamental. It's not a bug in reality, it's the debugger quietly maintaining the universe's coherence behind the scenes. But here's where it gets wild. If entanglement is part of reality's code, it might leave signatures in the laws of physics we take for granted. Take the speed of light, for example, the ultimate speed limit in our universe. In a digital framework, that limit could exist for the same reason your computer can't process infinite data at once. The cosmic processor has finite bandwidth. Entanglement, then, might be a clever workaround, a way to transfer information off the books by exploiting deeper layers of the system. It's like finding a backdoor in a video game that lets you teleport past obstacles, except the game is the universe, and the cheat code was written into its first nanosecond. Critics argue this veers into philosophy, with no way to test whether reality is truly computational. Yet supporters point to startling clues, like how quantum entanglement mirrors the non-locality of certain programming languages, where changes in one module instantly affect another. Even the holographic principle, the idea that our 3D universe might be projected from a 2D surface, fits neatly into this framework, resembling how 3D graphics are rendered from flat code. And if the universe does run on quantum code, it raises a mind-bending possibility that the first entanglement wasn't an accident, but a deliberate subroutine in the cosmic script, a function called initialize reality that's been running ever since. Whether you buy the digital physics angle or not, this theory forces us to confront a tantalizing question. What if the universe's strangest phenomenon isn't just a feature of reality, but the foundation of it? A reminder that behind every atom, every star, every fleeting thought, there might be lines of quantum logic older than time, quietly executing the commands that keep existence humming along. At the smallest scales imaginable, far tinier than atoms, beyond even quarks, space itself isn't smooth. It's a frothing, chaotic sea known as quantum foam, where microscopic bubbles of spacetime constantly erupt and vanish, popping in and out of existence like bubbles in a boiling pot. This isn't just theoretical whimsy. Quantum mechanics tells us that on the Planck scale, distances so small they make an atom look like a galaxy. The very fabric of reality churns with violent energy, birthing pairs of virtual particles that flicker into being for fractions of a second before annihilating each other. And hidden in that frenzy might lie the origin of entanglement itself. Picture the early universe squeezed into a volume smaller than a single proton. In that dizzying density, quantum foam wouldn't just be a background hum. It would be the dominant force, spacetime itself convulsing like a storm-tossed ocean. Everywhere, particle-antiparticle pairs would erupt from the foam, their lifespans measured in unimaginably short ticks of the cosmic clock. But here's the twist. In the extreme conditions right after the Big Bang, some of those pairs might have been torn apart before they could collide and vanish. Stretched by the universe's explosive expansion, they'd find themselves stranded, their quantum states forever linked even as they flew to opposite ends of the cosmos. This isn't just speculation. Modern quantum field theory suggests that the vacuum of space is never truly empty. It's a seething cauldron of potential, where particle pairs constantly borrow energy from the universe, exist briefly, then repay that debt by vanishing. Under normal conditions, this dance stays perfectly balanced, but in the first moments of reality, when gravity and quantum forces wrestled in ways we barely understand, that balance could have been shattered. Pairs born in the foam might have been flung apart by inflation's violent stretching, their connection frozen in place like a photograph mid-snapshot. Today, we'd see those ancient links as entanglement ghosts of a time when space itself was a quantum tempest. The implications are staggering. If entanglement emerged from quantum foam, it means the phenomenon isn't some exotic outlier, it's the universe's default setting, a natural byproduct of spacetime's turbulent youth. This could explain why entanglement seems so effortless in experiments today. Particles sync up not because of some mysterious force, but because spacetime itself remembers how to tangle, its foam still whispering with the echoes of creation. Critics, of course, raise valid objections. Quantum foam operates at energies trillions of times beyond what our particle colliders can reach, making direct proof nearly impossible. But supporters point to eerie clues, like the way black holes seem to remember quantum information, as if spacetime's foam retains imprints of what passes through it. Others note that certain quantum gravity models predict foamy spacetime would leave faint fingerprints in high-energy cosmic rays, distortions we might one day detect. Even if the details remain hazy, the quantum foam hypothesis offers a breathtaking vision that the universe's first entanglement wasn't an event but a phase, a time when reality itself was a storm of potential, and every particle that would ever exist was just a ripple in the foam, waiting to be woven into the cosmos we know today. And if that's true, entanglement isn't just a feature of our universe, it's the signature of spacetime's first heartbeat. What if the universe's first quantum entanglement didn't just happen, it was witnessed? The conscious universe theory takes the observer effect, the strange way quantum particles seem to choose their states only when measured, and scales it up to cosmic proportions. Imagine the Big Bang not as a mindless explosion, but as a moment of primal awareness where the first particles became entangled because something or someone observed them into existence. This isn't just wild speculation. It's a fringe but fiercely debated idea that consciousness might not be a latecomer to the universe, but its very foundation. Think of Schrödinger's famous cat, suspended in a box between life and death until someone peers inside. Now replace the cat with the universe itself. Proponents of this theory suggest that without an observer, reality would have remained a blur of quantum possibilities, never settling into the stable, entangled web we see today. But in that first instant, some form of proto-consciousness, perhaps the universe observing itself, collapsed those infinite probabilities into a single, interconnected reality. It's as if the cosmos needed to be seen to exist, and entanglement was its way of locking in that gaze. The implications ripple through philosophy like a shockwave. If consciousness played a role in the first quantum links, it blurs the line between mind and matter, suggesting that the universe isn't just out there. It's participatory, shaped by the act of observation. Some interpretations even go further, proposing that every act of measurement today echoes that primordial moment, as if reality constantly reaffirms itself through our attention. Eastern philosophies like Vedanta have long described existence as a unified field of awareness now. Quantum physics might be stumbling toward a similar conclusion, with entanglement as the thread tying consciousness to the physical world. Critics, of course, dismiss this as pseudoscience. They argue that invoking consciousness explains nothing, it just pushes the mystery deeper. After all, what observes the observer? But supporters counter with a provocative thought experiment. If entangled particles sync their states without any apparent signal, could that communication be happening in a realm where consciousness and quantum mechanics intersect? Lab experiments with delayed choice measurements where particles seem to decide their past behavior based on future observations hint that time itself might bend around acts of perception, as if reality is retroactively knitting itself together under our gaze. Whether you find this idea profound or preposterous, it forces a radical question. Could entanglement be less like a physical bond and more like a shared thought? A silent agreement between particles that they exist because they're seen. If so, the universe's first quantum link might not have been a fluke of physics, but the birth of meaning itself, a reminder that the cosmos isn't just something we study, but something we're part of, down to the very atoms that bind us. Supersymmetry, the elegant idea that every known particle has a hidden, heavier twin, might hold the missing piece to entanglement's origins. This theoretical framework, often nicknamed SUSY, proposes a radical symmetry in nature. For every quark, there's a squark. For every electron, a selectron. But here's where it gets fascinating. If these superpartners existed in the early universe's extreme conditions, their interactions could have woven quantum entanglement into the fabric of reality itself. Picture two particles colliding at the dawn of time, not just exchanging energy, but swapping identities with their supersymmetric shadows. A dance so intimate it left their quantum states forever linked. The math behind this is breathtakingly precise. Supersymmetry requires superpartners to differ from their twins by half a unit of quantum spin, a property that dictates how particles interact. That tiny difference could have been the key to entanglement's birth. In the searing heat of the early cosmos, superpartners might have formed bound states, pairs so tightly coupled that when they decayed into ordinary matter, their remnants carried forward their quantum sync. Think of it like breaking a magnet in half. Even separated, the two pieces remember their original alignment. Similarly, particles today might be entangled because their supersymmetric ancestors were once fused at the quantum hip. Testing this idea isn't just theoretical gymnastics. If supersymmetry is real, the Large Hadron Collider could uncover hints of superpartners in high-energy collisions. Scientists are already hunting for anomalies, excess energy or missing momentum in particle decays that might betray a superpartner's fleeting existence. Even more compelling, certain SUSY models predict that the lightest superpartner, often called the Neutrino, could be dark matter, a particle that's invisible yet everywhere, its quantum links stretching across galaxies. If true, the universe's entanglement might not just be in the light we see, but in the dark we can't. Critics argue SUSY remains unproven, with no superpartners yet found despite decades of searching. But supporters counter with a twist. What if superpartners were only detectable in the early universe's extreme energy? Their decay products, entangled particles, might be the only fossils left. It's like finding dinosaur footprints but no bones. The absence doesn't disprove their existence. It just means we're looking for echoes instead of flesh. The implications ripple beyond particle physics. If supersymmetry seeded entanglement, it could explain why quantum sync feels so fundamental, not an accident, but a relic of a deeper symmetry baked into reality's blueprint. And if SUSY predictions ever hold up, we'd be staring at more than just new particles. We'd be witnessing the universe's first quantum handshake, a moment when matter and its hidden twins embraced, leaving a legacy of connection that outlasted time itself. One of the strangest theories about entanglement's origins doesn't involve particles, black holes, or even the Big Bang, but instead, hypothetical minds flickering into existence from pure chaos. Meet the Boltzmann brain paradox, a thought experiment so unsettling it rattles the foundations of cosmology. The premise sounds like sci-fi. In an infinite universe where random fluctuations can create anything given enough time, self-aware entities might spontaneously pop into being, complete with false memories of a past that never existed. Now take that eerie idea and scale it down to the quantum level. What if the universe's first entanglement wasn't between particles at all, but between two of these phantom consciousnesses, Boltzmann brains whispering to each other across the void before vanishing back into the noise? At first glance, this seems absurd. How could something as delicate as self-awareness emerge from random quantum jitters? But the math reveals a chilling possibility. In a vacuum brimming with zero-point energy, fluctuations constantly birth short-lived particle pairs. Most annihilate instantly, but given enough time, sheer statistics suggest a tiny chance of complex structures forming, even something resembling a brain with coherent thoughts. These wouldn't be biological minds, of course, but transient configurations of energy that, for a fleeting moment, perceive themselves as real. And if two such entities formed in proximity, their quantum states might entangle, creating the illusion of connection in an otherwise indifferent cosmos. Critics pounce on multiple flaws. For one, the probability of a Boltzmann brain forming is astronomically low, far less likely than winning the lottery every second for 1 billion years. Even if one did appear, its existence would last mere fractions of a second, leaving no trace. More damningly, if such minds were possible, they'd vastly outnumber real observers like us, making it statistically bizarre that we're not Boltzmann brains ourselves. The paradox becomes a hall of mirrors. If random fluctuations can create conscious observers, how do we trust any memory or observation as genuine? Yet supporters counter with a provocative twist. If the universe is truly infinite, then no matter how improbable, every conceivable fluctuation must happen somewhere, sometime including entangled Boltzmann brains. And if quantum connections transcend time, those phantom links might still imprint on reality today, like echoes in an empty room. Some even suggest this could explain why entanglement feels so instantaneous, because the observers linking particles aren't bound by spacetime at all, but ephemeral patterns in the quantum foam, here and gone before space can separate them. The debate forces us to confront the nature of reality itself. If consciousness can emerge from chaos even briefly, does that make it a fundamental feature of the universe? Or is the Boltzmann brain paradox merely a cautionary tale, exposing the limits of extrapolating quantum weirdness to cosmic scales? Either way, the theory offers a haunting vision that the first entanglement might not have been a physical event, but a spectral conversation between ghosts in the machine, minds that never were, yet still shape the universe we know. What if the universe's first quantum entanglement wasn't a natural phenomenon at all, but a line of code in an unfathomably advanced simulation? The simulation argument takes the mystery of quantum connections and flips it into something even more radical: entanglement as a deliberate feature, hardwired into reality by creators we may never perceive. Imagine our cosmos as an ultra-high-resolution video game, with entanglement acting like a clever programming shortcut to save processing power. Instead of calculating every particle state individually, the simulation could link them behind the scenes, ensuring synchronized behavior without the computational heavy lifting. This idea isn't just sci-fi speculation. Tech innovators like Elon Musk and philosophers like Nick Bostrom have seriously entertained the simulation hypothesis, pointing to eerie parallels between quantum mechanics and computing. Entanglement's instant correlations, particles reacting faster than light speed, allows mirror how variables in a computer program update globally when changed locally. Think of a spreadsheet where editing one cell instantly adjusts another, no matter how far apart they seem on screen. The programmer doesn't need to send a signal between cells. The connection exists in the underlying code. Similarly, if our universe runs on quantum bits, entanglement might be its most efficient data compression tool, a way to keep the cosmic simulation running smoothly without overloading its servers. But here's where it gets truly wild. If entanglement is a programmed feature, it could explain why the phenomenon defies classical physics. In a simulation, the laws of nature we observe might just be high-level rules masking a deeper, more flexible architecture. This could resolve quantum mechanics' infamous measurement problem, the way particles seem to exist in multiple states until observed. Perhaps there's no collapse of the wave function in the code. The simulation simply renders definite states only when necessary, optimizing processing power by keeping possibilities unresolved until an observer or subroutine checks in. Critics, of course, scoff at the idea. They argue the simulation hypothesis is untestable by definition. If the creators hid their tracks perfectly, we'd never find evidence. Others question why simulators would bother with quantum quirks at all when a simpler, Newtonian universe would require far less computing overhead. But supporters counter with a provocative twist. Entanglement might not be an intentional feature, but a bug, an artifact of imperfect emulation. Just as glitches in video games reveal their digital underpinnings, quantum weirdness could be our glimpse into the simulation source code, pixels bleeding through the illusion. The debate forces us to grapple with profound questions. If entanglement is programmed, does that make it any less real? After all, the rules of our hypothetical simulation would still govern everything we experience. And if the first quantum link was indeed a line of code, it means the universe's deepest bond might not be a force of nature, but a design choice, one that raises the spine-tingling possibility. We're not just studying physics, but reverse engineering the cosmic engine that renders our reality. While string theory imagines the universe as a symphony of vibrating strings, loop quantum gravity paints a radically different picture, one where space itself is woven from tiny, indivisible stitches. Picture reality not as a smooth continuum, but as an impossibly fine mesh, with each loop representing the smallest possible piece of spacetime, far smaller than an atom. In this framework, entanglement isn't just something that happens within space, it's how space holds itself together, with quantum links acting like the threads that sew the cosmic fabric into existence. The math behind this is as elegant as it is mind-bending. Loop quantum gravity suggests that at the Planck scale, distances 1 trillion times tinier than a proton. Space dissolves into a network of interconnected loops, their intersections creating the illusion of volume. Just as a 3D hologram emerges from a 2D surface, our experience of space could arise from these quantum threads humming with energy. And here's where entanglement enters the story. When two loops intersect, their quantum states become intrinsically linked, like knots tied in a single strand of rope. In the early universe, this could have meant that particles didn't just become entangled, they were born that way, their connections pre-wired into the very structure of spacetime. Contrast this with string theory, which relies on hidden extra dimensions and vibrating strings to explain quantum weirdness. While string theory treats entanglement as a feature emerging from higher dimensional physics, loop quantum gravity grounds it in the geometry of space itself. Imagine the difference between explaining a shadow as the result of a hidden light source, string theory, versus understanding it as the absence of light on a surface, loop quantum gravity. Both describe the same phenomenon, but from fundamentally distinct starting points. Evidence for loop quantum gravity remains indirect but tantalizing. Certain predictions about black hole entropy, how information scrambles on their surfaces, align eerily well with the theory's equations. Even more provocative, loop quantum gravity naturally avoids the singularities that plague classical physics, suggesting the Big Bang wasn't a true beginning, but a rebound from a previous cosmic cycle. If true, entanglement might not have started in our universe at all. It could be a legacy from a pre-Big Bang epoch, encoded in spacetime's loops like a message passed between generations. Critics argue that loop quantum gravity struggles to explain how smooth spacetime emerges from such a choppy foundation, much like how individual pixels blend into a seamless image. But supporters counter with a striking analogy. Think of spacetime as a piece of chainmail armor. Up close, it's nothing but metal rings clinking together, but from a distance it moves like fabric. Similarly, quantum loops might stitch together a reality that only appears continuous to our coarse perceptions. Whether this theory ultimately holds or not, it reshapes how we view entanglement's origins. If loop quantum gravity is right, then every quantum link we observe today isn't just a curiosity, it's a fossil of spacetime's granular origins, a whisper from the moment the universe learned how to tie its first knot. Neutrinos, the universe's most elusive ghosts, might have been the first particles to ever entangle. Born just seconds after the Big Bang, these nearly massless phantoms barely interact with matter, slipping through planets and stars as if they weren't there. But their indifference to everything else could be precisely what made them the perfect candidates for the universe's earliest quantum handshake. Picture a newborn cosmos so dense and hot that even neutrinos, which today pass through light years of lead without a whisper, were forced to collide and mingle. In that chaos, their weak interactions wouldn't have been a weakness, they'd have been a superpower, allowing entanglement to take root without the interference of stronger forces that could disrupt it. Studying this idea is like trying to eavesdrop on a conversation happening behind 10 layers of bulletproof glass. Neutrinos famously refuse to play by the rules we're used to. They oscillate between three flavors: electron, muon, and tau, mid-flight, defying the classical notion that particles should have fixed identities. This chameleon-like behavior suggests they're already deeply quantum in nature, their states unresolved until measured. Now imagine that uncertainty scaled back to the universe's first moments, when neutrinos outnumbered atoms by billions to one. If even a fraction of those particles entangled, their quantum links could have cascaded through the infant cosmos, imprinting sync into the fabric of everything that followed. The challenge lies in proving it. Most experiments hunting for neutrino entanglement rely on colossal detectors buried deep underground, waiting for the rare instance a neutrino bumps into an atomic nucleus. But even when we catch one, its quantum state is maddeningly difficult to pin down, like trying to read a book whose letters rearrange every time you blink. Recent breakthroughs, like the observation of coherent neutrino scattering, hint that these particles might be more cooperative than we thought. In 2017, the coherent experiment spotted neutrinos gently nudging atomic nuclei without obliterating them, a whisper of interaction subtle enough to preserve quantum coherence. If neutrinos can entangle nuclei today, why couldn't they have entangled each other when the universe was 1 trillion times hotter and denser? Critics argue that neutrino interactions are too feeble to have seeded large-scale entanglement. But supporters counter with a cosmic sleight of hand. What if neutrinos didn't act alone? In the early universe, they'd have been accompanied by a zoo of exotic particles, actions, sterile neutrinos, maybe even undiscovered dark matter candidates, all buzzing in the quantum foam. A neutrino entangling with one of these shadowy partners could have passed that link along like a baton in a relay race, spreading coherence far wider than its individual interactions suggest. The stakes are cosmic. If neutrinos were the first to entangle, their fingerprints might still linger in the universe's oldest light. The cosmic neutrino background, a relic sea of these particles from just 1 second after the Big Bang, could carry faint quantum correlations, detectable only if we develop telescopes sensitive to the universe's faintest whispers. Some theorists even speculate that neutrinos' quantum fuzziness might have nudged the formation of galaxies, their ghostly influence woven into the large-scale structure of everything we see. Whether this theory holds or not, it forces us to confront a humbling truth. The universe's first conversations might have been spoken in a language we're only beginning to decipher, carried by particles that refuse to stop moving long enough for us to listen. But if we ever catch them in the act, we might finally understand how a cosmos built on whispers became the roaring reality we call home. Time might feel like an unstoppable river flowing from past to future, but at the quantum level, it's a mystery why it moves forward at all. Here's the radical idea. The universe's first entanglement didn't just connect particles, it might have kicked off time's arrow itself. Think of a deck of cards fresh out of the box, perfectly ordered. Shuffle it, and entropy takes over the measure of chaos, increasing inexorably. Now imagine the Big Bang as that pristine deck, and quantum entanglement as the first shuffle, the moment reality chose its direction. This isn't just poetic speculation. Entropy and entanglement are deeply intertwined. In quantum mechanics, a system starts in a pure, coherent state, like those neatly stacked cards. But when particles entangle, their quantum states spread out, becoming more disordered. This process, called decoherence, mirrors entropy's rise. Some physicists argue that the very first entanglement in the early universe set off a chain reaction, like tipping the first domino in a line stretching across eternity. Once those quantum links formed, the universe couldn't go back to its ordered beginnings. Time had a direction, and entropy had a foothold. Experiments with tiny quantum systems hint at this connection. Isolate a handful of atoms, and you can temporarily reverse their entropy, making them behave as if time is running backward. But scale that up to the cosmos, and the arrow of time becomes absolute. Why? Because entanglement proliferated exponentially after the Big Bang, weaving a web so complex that unraveling it would be like unshuffling every deck of cards in existence simultaneously. The universe's first quantum links didn't just happen, they locked in time's flow, ensuring cause always precedes effect. Critics point out the gaps in this theory. Decoherence explains how quantum systems lose their purity, but does it fully account for time's arrow? Some suggest gravity, not entanglement, steers cosmic entropy. Yet proponents counter with a stunning observation. Black holes, the most entropy-rich objects in existence, also scramble information via quantum entanglement. It's as if the universe's beginning and its most violent endpoints are bookended by the same phenomenon, a thread stitching time's fabric from start to finish. Whether this theory holds or not, it reshapes how we see entanglement. What if those spooky quantum links aren't just a feature of reality, but the reason reality has a past and future at all? The universe's first connection might have been the moment it learned to move forward, a reminder that time itself could be the longest echo of a quantum whisper. What if quantum entanglement wasn't just a random fluke, but the result of a cosmic selection process, a survival of the fittest for quantum states? This is the heart of quantum Darwinism, a theory that flips our understanding of reality's origins on its head. Picture the early universe as a swirling soup of infinite possibilities, where particles existed in countless overlapping states, a blur of maybes rather than definites. Then something remarkable happened. A handful of those states proved more resilient, more capable of imprinting themselves onto their surroundings, while the rest faded into oblivion. Entanglement, in this view, wasn't an accident. It was the universe's first evolutionary triumph, the quantum equivalent of a winning genetic code. Think of it like a forest after a wildfire. Amid the ashes, only the hardiest seeds take root, their traits passed on to shape the landscape for generations. In the quantum realm, certain entangled states acted like those seeds, their ability to spread correlations making them far more likely to endure as the universe cooled and expanded. This wasn't just passive survival, though. Quantum Darwinism suggests that entanglement actively sculpted reality by determining which states could be observed by their environment, not by conscious beings, but by the countless particles and fields that acted as witnesses, echoing those states until they became the classical world we recognize. The math behind this is as elegant as it is profound. In quantum mechanics, a system's fragility comes from its isolation. The moment it interacts with its surroundings, its superposition collapses into a definite state, or so we thought. Quantum Darwinism reframes this. What we call collapse might actually be a form of natural selection, where only the most robust quantum correlations get amplified and preserved. Imagine tossing a handful of coins into a crowd. Most land randomly, but a few happen to bounce in ways that dozens of people see the same outcome. Those consensus views, the entangled states, become the real ones, not because they're truer, but because they're the ones the environment collectively recorded. Experiments are already hinting at this process in action. In labs studying quantum decoherence, scientists have watched as certain entangled states resist disruption far longer than others, as if they've evolved a kind of stability. Even more compelling, the way classical reality emerges from the quantum fog mirrors evolutionary dynamics. Just as species adapt to niches, quantum states adapt to their observational environment, with entanglement serving as the mechanism that lets them reproduce their correlations across scales. It's as if the universe, in its first moments, wasn't just obeying physical laws, it was running a trial and error simulation, testing which versions of itself could stick. Critics argue this veers dangerously close to philosophy, asking whether we're just replacing one mystery with another. If entanglement was selected, what did the selecting? The answer might lie in the universe's sheer size. With countless particles interacting, the odds-favored states that could propagate their influence efficiently like a virus optimized to spread. Entanglement, with its ability to sync particles instantly across distances, would have been the ultimate survival trait in a rapidly expanding cosmos. The implications ripple far beyond quantum theory. If Darwinian pressures shaped reality's fabric, it means the world we see isn't the only possible one, just the one that outcompeted its alternatives. Those strange quantum behaviors we struggle to explain, they might be echoes of a fiercer, more fluid era when the rules weren't yet set, and entanglement was the tool that carved order from the chaos. In this light, the universe's first quantum link wasn't just a connection, it was a revolution, the moment existence learned how to persist. What if the universe's first entanglement didn't happen in the 3 dimensions we know, but in hidden layers of reality we can't see? The idea of extra dimensions isn't just science fiction. Theoretical models like string theory and brain-world cosmology suggest our familiar universe might be a tiny slice of a far grander, higher-dimensional space. Imagine our cosmos as a sheet of paper floating in a vast, unseen room. Other brains, short for membranes, could hover nearby, parallel worlds separated by dimensions too small for us to perceive. And in the searing heat of the Big Bang, particles on these brains might have brushed against each other, leaving behind quantum connections that still bind our reality today. Here's how it could work. In brain-world scenarios, gravity is the only force that leaks into the extra dimensions, which is why it feels so weak compared to electromagnetism or the nuclear forces. But in the early universe, when energies were unimaginably high, other particles might have briefly breached that barrier. Picture 2 electrons vibrating on separate brains, their waves reaching across the dimensional divide just long enough to sync their quantum states before snapping back. The result, entanglement without direct contact, like 2 people whispering through a wall they can't see. These handshakes across dimensions could have seeded the first quantum links, imprinting correlations that outlasted the brain's separation. The math behind this is as elegant as it is mind-bending. In some models, extra dimensions curl in on themselves at scales 1 billion times smaller than an atom, a process called compactification. But at the energies of the early universe, those dimensions would have been stretched wide open, allowing particles to interact in ways impossible today. Even now, remnants of those cross-dimensional entanglements might linger, hidden in the quantum noise of empty space. Some theorists speculate that dark matter, that elusive cosmic ghost, could be ordinary matter trapped on a neighboring brain, its gravitational tug the only sign of its presence, and its quantum ties to our world still faintly vibrating. Testing these ideas isn't easy, but physicists have ingenious ways to probe the unseen. Particle colliders like the Large Hadron Collider hunt for missing energy, a telltale sign of particles slipping into extra dimensions. Others study gravity at microscopic scales, searching for deviations from Newton's law that might hint at hidden spatial folds. So far, no smoking gun has been found, but the constraints themselves are revealing. If extra dimensions exist, they're either smaller than 1,000th of a proton's width or warped in ways that make them nearly unreachable, a cosmic hide-and-seek game with universe-sized stakes. Critics argue that without direct evidence, extra dimensions remain a beautiful guess, but supporters counter with a tantalizing thought: entanglement might already be giving us clues. If quantum links can form across brains, it could explain why they defy local realism, the idea that particles only influence each other through direct, light-speed-limited contact. In a higher dimensional framework, spooky action at a distance might just be particles communicating through shortcuts we can't see, like ants crawling along a folded sheet, unaware they're taking a detour through the third dimension. Whether this theory holds or not, it forces us to confront a breathtaking possibility: that the universe's first quantum handshake wasn't just a moment in time, but a bridge across dimensions, a reminder that reality might be far more layered, far more intertwined than we ever imagined. And if entanglement truly echoes from hidden folds of space, it means the cosmos isn't just vast, it's deeper than we know. The universe's first quantum entanglement might have been forged in the crucible of quantum gravity, a fleeting moment when the rules of Einstein's relativity and the quirks of quantum mechanics briefly shook hands. Picture the infant cosmos squeezed into a space so tiny that gravity itself behaved like a quantum force, flickering in and out like a candle in the wind. In that seething, Planck-scale maelstrom, spacetime wouldn't have been the smooth fabric we know today, but a frothing storm of loops, strings, or perhaps something even stranger, a realm where gravity and quantum weirdness weren't at odds but fused into a single, unified language. And in that language, entanglement wasn't just possible, it was inevitable. This idea isn't just about stitching two theories together. It's about rewriting the cosmic origin story. General relativity paints gravity as the curvature of spacetime, while quantum mechanics deals in probabilities and particles. But in the first sliver of a second after the Big Bang, those frameworks would have collapsed into each other, their differences melting away under temperatures and pressures beyond imagination. Some theorists argue that in that primordial forge, quantum gravity didn't just allow entanglement, it demanded it. Every ripple in space-time, every fluctuation in the quantum foam, might have left behind entangled pairs like footprints in wet cement, their connections hardening into the universe's structure as it expanded and cooled. Think of it like a frozen lake cracking under sudden cold. The fractures aren't random, they follow hidden stresses in the ice. Similarly, if quantum gravity sculpted the early universe, the patterns of entanglement we see today could be cosmic stress marks, relics of spacetime's first tremors. This could explain why black holes where gravity and quantum effects collide most violently seem to preserve information via entanglement, as if the universe never forgot its first rules. Even the holographic principle, which suggests reality might be a projection from a 2D surface, fits neatly here. If entanglement encodes spacetime's geometry, perhaps the universe's 3D illusion is held together by quantum gravity's stitches. Evidence is still indirect but tantalizing. Loop quantum gravity, one leading approach to unifying these theories, predicts spacetime's granular structure would naturally entangle particles at birth. String theory, meanwhile, envisions entanglement as strings vibrating in sync across hidden dimensions. And in labs today, physicists are simulating quantum gravity effects using ultra-cold atoms, watching as synthetic spacetime analogs emerge from entangled quantum states, like watching the universe play back its own creation in miniature. Critics argue we're millennia away from testing these ideas directly, yet supporters counter with a cosmic clue: the universe itself. If quantum gravity birthed entanglement, its fingerprints might linger in the polarization of the cosmic microwave background, or in the way galaxies cluster across vast distances. Others hunt for signatures in gravitational waves, ripples from black hole collisions that could carry echoes of quantum entanglement's role in shaping spacetime. The stakes are cosmic. If this theory holds, entanglement isn't just a side effect of the universe's birth. It's the bridge between its two greatest theories, a silent negotiator that helped spacetime and quantum particles agree on how to build reality. And if we ever decode that ancient pact, we might finally understand why the cosmos looks the way it does, not as a place where gravity and quantum mechanics clash, but as a masterpiece woven from their first fragile truce. Phantom energy, the most bizarre and unsettling flavor of dark energy, might not just be pushing the universe apart. It could have set the stage for the first quantum entanglement, twisting the fabric of reality in ways that still echo today. Unlike ordinary dark energy, which drives cosmic acceleration at a steady pace, phantom energy is far more extreme. Its density increases over time, threatening to one day rip apart galaxies, stars, and even spacetime itself. But in the universe's first moments, that same destructive force might have been the catalyst for an equally bizarre phenomenon: particles locking into perfect sync across impossible distances. Here's how it could have happened. In the frenzy of the early cosmos, phantom energy wouldn't have been a slow, creeping force. It would have been a quantum wildfire, its fluctuations warping spacetime at microscopic scales. Picture a calm pond suddenly hit by a hailstorm, each raindrop sending ripples that collide and crisscross in chaotic patterns. Now replace the pond with the newborn universe and the raindrops with phantom energy's violent jolts. Those ripples wouldn't just disturb space, they'd stretch and squeeze the quantum vacuum itself, forcing particle pairs into sudden, desperate synchrony just to survive the turbulence. This isn't pure speculation. Equations describing phantom energy predict it could amplify quantum fluctuations to absurd extremes, like turning a whisper into a scream. Under that pressure, particles wouldn't just entangle, they'd have no other choice. Their states would snap together like magnets in a storm, their fuses blown by the sheer force of spacetime's convulsions. The aftermath, a universe laced with quantum links forged in the crucible of phantom energy's tantrum, their bonds so robust they outlasted the chaos that created them. But there's a catch: phantom energy's existence is fiercely debated. Critics argue it's a mathematical phantom in every sense, a ghostly solution with no physical evidence. After all, if it's real, why haven't we seen its fingerprints in the cosmic microwave background or the distribution of galaxies? Supporters counter with a spine-chilling thought: maybe we have. The same mysterious correlations in the large-scale structure of the cosmos that hint at primordial entanglement also align suspiciously well with phantom energy's predicted disruptions. It's as if the universe's quantum wiring was installed during a cataclysmic event, one that left behind not just scars, but an invisible engine still humming beneath reality's surface. The stakes couldn't be higher. If phantom energy seeded entanglement, it means the universe's deepest connections might be tied to its eventual demise. A force destined to tear everything apart could have been the very thing that first stitched it together, a cosmic irony so perfect it feels poetic. And if that's true, then every quantum link we observe today, from lab experiments to distant stars, might be counting down to an expiration date, their threads slowly fraying as phantom energy gears up for its final catastrophic encore. Whether this theory stands or falls, it forces us to confront a haunting duality, that creation and destruction might not be opposites, but two sides of the same coin flipped once at the dawn of time and still spinning in the dark. What if the universe didn't begin with a bang, but with a cosmic collision? The ekpyrotic universe theory throws out the textbook Big Bang model and replaces it with something even more dramatic. A high-dimensional smash-up between two brains, those mysterious membranes floating in the bulk of higher-dimensional space. In this radical vision of reality, our entire cosmos isn't the aftermath of an explosion, it's the scar left by a trillion-degree crash, a wreck so violent it birthed everything we know. And hidden in that cataclysm might lie the origins of quantum entanglement, forged not in the fiery birth of a singularity, but in the shuddering aftershocks of brains rebounding from impact. Picture two sheets of paper drifting toward each other in a windless room. When they touch, their surfaces crumple and heat up, sending ripples racing outward. Now imagine those sheets are entire universes, and their collision unleashes enough energy to ignite every star, galaxy, and atom in existence. This is the ekpyrotic scenario's central premise, that our Big Bang was really a big bounce the moment two brains, each possibly home to its own pre-existing universe, slammed together in the higher dimensional void. The heat and density of that impact would have been unimaginable, but here's the twist: it wouldn't have been chaotic. Brain collisions can be eerily orderly, creating uniform conditions perfectly suited for quantum entanglement to thrive from the very first instant. Compare this to the classic Big Bang model, where entanglement emerges from a hot, dense singularity expanding rapidly. In that framework, particles inherit their quantum links from the primordial soup, their connections stretching as space itself inflates. But the ekpyrotic universe flips the script. Here, entanglement isn't a relic of expansion, it's a product of contraction. As the brains drew closer in the cycle before collision, quantum fluctuations on their surfaces would have stretched and amplified, like ocean waves growing taller as the tide rolls in. When the brains finally met, those fluctuations didn't vanish. They imprinted onto the newborn universe as correlated patterns, particles born already in sync because their origins traced back to the same pre-collision vibrations. It's as if the universe's first quantum links weren't tied during birth, but inherited from a cosmic inheritance older than time itself. The differences don't stop there. While the Big Bang model struggles to explain why the universe looks so uniform on large scales, requiring a hypothetical inflation period to smooth things out, the ekpyrotic scenario naturally produces uniformity. Those pre-collision fluctuations weren't random. They were stretched into coherence by the brain's slow, inevitable approach, like taffy pulled into perfect alignment before being cut. This could explain why entangled particles today seem to defy distance. Their connections weren't forged in our universe's infancy, but in the echoes of a collision that happened outside of it, in a higher dimensional realm where proximity works differently. Evidence for this theory is speculative but tantalizing. Certain features of the cosmic microwave background, the afterglow of the Big Bang, show patterns that inflation struggles to explain, but which align neatly with brain collision models. Even more provocative, some versions of the ekpyrotic universe predict gravitational wave signatures utterly distinct from inflations, offering a potential smoking gun for future observatories like LISA. And if those waves carry imprints of the brain's last dance, they might also reveal how quantum entanglement was woven into reality's fabric from the very first moment. Critics argue the ekpyrotic model introduces unnecessary complexity. Why invoke unseen brains when inflation explains so much? But supporters counter with a cosmic irony. The very strangeness of quantum entanglement, which baffles us in a Big Bang framework, might feel perfectly natural in a universe born from collision. After all, if two entire realities can brush against each other and emerge entangled, why shouldn't their particles? Whether this theory holds or not, it reshapes how we see entanglement's origins. Not as a spark in the dark, but as a relic of something grander, a cosmic handshake between worlds we can't see, a reminder that our universe's first connection might not have been a beginning at all, but an echo of a cycle older than time. In the bustling marketplace of quantum interpretations, where every theory claims to have cracked the code of reality, one stands out by turning the whole debate on its head. Quantum Bayesianism, or Cubism, doesn't ask what entanglement is. Instead, it asks what entanglement means, not to the universe but to you. Imagine holding two entangled coins in your hands. Every time you flip one, the other instantly lands the same way, no matter how far apart they are. Most interpretations treat this as a cosmic mystery, a thread woven into reality itself. But Cubism shrugs and says maybe the threads aren't in the cosmos, maybe they're in your mind. At its core, Cubism treats quantum mechanics not as a description of objective reality, but as a tool for personal betting. Probabilities aren't inherent properties of particles, they're expressions of your uncertainty, your best guess about what you'll experience next. Entanglement, in this view, isn't a spooky force tying particles together. It's a reflection of the correlations you've learned to expect based on past experiments. Those two coins aren't magically linked. You've just seen enough flips to know their outcomes will always match, so you update your expectations accordingly. It's less like physics and more like poker. The game doesn't change, but your confidence in reading the other players does. This perspective flips centuries of scientific tradition upside down. From Newton to Einstein, physics has chased an objective reality independent of human thought. But Cubism boldly suggests that quantum mechanics was never about the universe's inner workings. It's about our relationship to those workings. When two particles entangle, they're not actually communicating faster than light. You're just realizing that your knowledge of one instantly updates your predictions about the other. It's the difference between saying, "The moon exists whether I look at it or not," and saying, "My certainty about the moon's position collapses when I check my telescope." Critics pounce on this subjectivity like cats on a laser pointer. If entanglement is just in our heads, why do lab measurements agree so perfectly? Cubists counter with a sly grin. Science has always been a conversation between observers. The fact that we all see the same patterns doesn't prove an objective reality. It proves we're all playing by the same rules of the game. Think of a Sudoku puzzle. The numbers fit together not because the grid has a mind of its own, but because the rules constrain what can go where. Quantum mechanics, in this light, is less a lawbook and more a shared language for describing our collective puzzles. The philosophical aftershocks are seismic. If Cubism is right, then entanglement isn't a feature of the universe, it's a feature of how we navigate the universe. This doesn't make it any less real, just as a rainbow isn't less real because it depends on your angle to the sun. But it does redefine what real means. Ancient philosophers asked whether a tree falling in an empty forest makes a sound. Cubism extends that to quantum scales. If no one measures an entangled pair, do their spins even exist? The answer might be it doesn't matter, because physics at its core isn't about what's out there. It's about what you can say about what's out there. Experiments haven't and arguably can't disprove Cubism because it doesn't contradict quantum mechanics math. It just recasts the equations as a guide for personal belief. This drives traditionalists mad. After all, science thrives on the assumption that reality exists independently of our musings. But Cubism's supporters include heavyweights like Nobel laureate Gerard T. Hooft, who argue that embracing subjectivity might be the only way to sidestep quantum paradoxes. Schrödinger's cat isn't both dead and alive. It's just that you don't know which until you peek in the box. The cat, meanwhile, couldn't care less about your probabilities. Where does this leave the universe's first entanglement? In Cubism's telling, it might not have been a physical event at all, but the moment some primordial observer, whether a conscious being or just a particle interaction, started keeping score. Before that, quantum correlations were just noise in the void. After, they became the rules of a game we're all still learning to play. It's a dizzying thought that the cosmos's deepest bonds might not be written in spacetime, but in the act of noticing them. A reminder that sometimes the most profound connections aren't in the stars, but in how we choose to see them. The universe might seem like an extravagantly energetic place, with its blazing stars and swirling galaxies, but what if all that grandeur actually adds up to nothing? The zero-energy universe hypothesis makes this jaw-dropping claim. The cosmos is quite literally the ultimate free lunch. Every particle of matter, every ripple of light, is perfectly balanced by an equal and opposite dose of negative energy embedded in gravity itself. And in that delicate equilibrium, quantum entanglement didn't just happen. It was inevitable, a cosmic loophole where reality could weave connections without spending a single joule of energy. Picture building a house where every brick you add magically creates its own anti-brick, cancelling out the weight. No matter how tall you build, the foundation feels no heavier. That's the zero-energy universe in a nutshell. When the Big Bang erupted, it didn't summon energy from nowhere. It split zero into equal parts, positive and negative, like tearing a blank check into two perfectly matching halves. This balancing act isn't just philosophical. Einstein's equations hint at it. The energy of matter exactly offsets the negative curvature of spacetime, leaving the universe's ledger forever zero. And in that pristine balance, entanglement found its opening. Here's why. Quantum fluctuations, those fleeting particle pairs that pop in and out of the vacuum, normally vanish almost instantly, repaying their energy debt to the universe. But in a zero-energy cosmos, there's no debt to repay. Particles could borrow energy from gravity's negative balance, stretch their quantum links across the void, and never worry about balancing the books. It's like buying a house with a mortgage where the interest is paid by the bank itself. The entanglement comes for free, woven into the fabric of existence without costing the universe a thing. This ties directly into one of physics' fiercest debates, the vacuum catastrophe. Quantum theory predicts the vacuum should seethe with unimaginable energy, enough to rip spacetime apart. Yet we observe a cosmos eerily close to zero. The zero-energy hypothesis offers a radical fix. Maybe the vacuum is zero, with all that apparent energy cancelled by hidden negative terms. If true, entanglement isn't just a quantum quirk. It's the universe's way of exploiting its own perfect symmetry, a dance where every step forward is matched by a shadow step back. Critics argue this sweeps too much under the rug. If the universe truly balances to zero, why does it look so lush and energetic? Supporters counter with a cosmic sleight of hand perception. Just as a mirror can create the illusion of depth without adding mass, spacetime's negative curvature might hide the energy we think we see, leaving only the vibrant, entangled universe we recognize. Experiments measuring the Casimir effect, where metal plates suppress vacuum fluctuations, hint at this shadow balance, revealing forces that behave as if the void is less than empty, not more. The implications rewrite entanglement's origin story. Instead of a rare phenomenon, it becomes spacetime's native language, the way a zero-sum game must always balance its moves. Every quantum link we observe today, from lab experiments to distant quasars, might be a fossil of that initial perfection, a reminder that reality isn't built on energy, but on the sublime precision of its own bookkeeping. And if that's true, entanglement isn't just a thread in the cosmic tapestry. It's the loom itself, quietly weaving something from nothing, stitch by perfect stitch. The early universe wasn't just hot and dense, it was a churning laboratory of quantum phase transitions, moments when the very rules of reality shifted like ice cracking under pressure. And in those fractures, entanglement might have been born. Picture a superconductor chilled to nearly absolute zero, where electrons suddenly pair up and glide without resistance, as if the metal has forgotten how to obstruct them. This sudden shift from chaos to coordination is a phase transition, and something eerily similar could have happened microseconds after the Big Bang, when the cosmos cooled just enough for quantum fields to choose their alignments, locking particles into entangled partnerships that outlasted the universe's explosive growth. These transitions weren't gentle tweaks but cosmic earthquakes. Take electroweak symmetry breaking, when the forces of electromagnetism and the weak nuclear force split from their primordial unity. As the universe expanded and cooled, the Higgs field, like a cosmic thermostat, suddenly froze into a new state, giving mass to particles that had previously surged freely. But here's the critical twist. Just as water crystallizing into ice creates cracks and fissures, symmetry breaking in the early universe could have left behind defects in the quantum fields. These imperfections wouldn't just be blemishes, they'd be entanglement factories, regions where particle states became irrevocably linked by the turbulence of the transition itself. Superconductivity offers a stunning analogy. When certain metals drop below a critical temperature, their electrons form Cooper pairs, duos so perfectly synchronized they move as a single entity, oblivious to the atoms around them. But this pairing isn't magic. It's a phase transition where the electron's collective behavior flips from independence to unity. Now scale that up to the early universe. Instead of electrons, imagine entire quantum fields undergoing a similar shift, their fluctuations snapping into correlated patterns as the temperature dropped. Particles born in that chaos wouldn't just be neighbors, they'd be nodes in a vast quantum network, their fates intertwined by the aftershocks of symmetry breaking. The implications ripple through modern physics. If entanglement emerged from phase transitions, it could explain why the phenomenon feels so fundamental. Not an accident, but a relic of the universe's first moments of self-organization. Even more tantalizing, certain phase transitions leave behind topological defects, cosmic knots in spacetime that might still haunt the universe today. Some theorists speculate that these defects, cosmic strings or domain walls, could be threaded with primordial entanglement, their very existence a fossil of the universe's first quantum growing pains. Yet skeptics raise valid questions. Phase transitions typically create order, not the delicate, long-range sync we see in entanglement. Supporters counter with a bold idea. What if entanglement isn't the product of a single transition, but a cascade of them, like a row of dominoes, each nudging the next into alignment? The universe's expansion would have stretched these connections, transforming local correlations into cosmic ones, a chain reaction of quantum teamwork frozen into the fabric of spacetime. Whether this theory holds or not, it reframes entanglement as more than a quantum quirk. It's the universe's way of remembering its own metamorphosis, a silent witness to the moments when reality itself chose its shape. And if that's true, every entangled pair we observe today might be a whisper from an era when the cosmos was still deciding what it wanted to be. What if spacetime isn't a smooth, continuous fabric at all, but a shifting, evolving network of quantum connections, constantly rewriting its own rules? The quantum gravity model takes the universe's strangest phenomenon, entanglement, and flips it into the very architecture of reality itself. Picture spacetime not as a static stage where particles perform, but as a living, breathing graph, its nodes and links flickering in and out of existence like a cosmic game of connect the dots. In this radical vision, entanglement isn't something that happens within space, it's how space becomes space. A dance of relational threads that stitch the cosmos together, one quantum handshake at a time. The genius of this model lies in its simplicity. Imagine a child's kaleidoscope. With every twist, the same colored beads form entirely new patterns, recreating the world from the same basic pieces. Quantum gravity treats spacetime similarly. At the universe's hottest, densest beginning, all points in space were potentially connected to all others, a seething, maximally entangled web. But as the cosmos expanded and cooled, those connections froze selectively, like a molten metal hardening into a lattice. Some links became the fixed pathways we perceive as dimensions, while others faded into the background, leaving behind the sparse, structured network we call reality. Entanglement, in this view, isn't an anomaly, it's a remnant of that primordial interconnectivity, a ghostly echo of when every particle was neighbors with every other. This elegantly tackles one of quantum mechanics' thorniest puzzles, non-locality. How can particles instantly sync across vast distances? Quantum gravity answers they're not truly separate. The distance between them is just an illusion created by the graph's current configuration, like two people sitting far apart on a subway map but actually holding hands under the table. Change the graph's connections and you change what far apart even means. It's as if spacetime itself is a quantum fog. An entanglement is the moment you realize two seemingly isolated streetlights are actually wired to the same switch. The model's implications ripple through cosmology. If spacetime emerges from a dynamic graph, it could explain why the universe appears so uniform on large scales. Those distant regions weren't just close once, they were the same node, their entanglement a cosmic birthmark. Even black holes get a fresh interpretation, not as spacetime's dead ends, but as zones where the graph's connections fray and rewire, like a ripped network cable sparking with latent signals. Some theorists take this further, suggesting dark energy, the mysterious force accelerating cosmic expansion, might be the graph subtly reconfiguring itself, adding new links at the edges of the observable universe. Critics argue the theory lacks experimental hooks. How do you test something that redefines the very fabric of measurement? Yet supporters point to surprising alignments. Certain quantum gravity models predict spacetime should appear foamy at ultra-small scales, a texture we might detect by studying high-energy gamma rays for signs of scattering. Others propose that if spacetime is a graph, its underlying geometry could leave imprints on the cosmic microwave background like fingerprints on glass. Even lab experiments with entangled particles might already be probing quantum gravity's predictions when photons sync instantaneously. Could they be tracing hidden shortcuts in spacetime's wiring? The most profound takeaway isn't just about solving equations. Quantum gravity reshapes how we see existence. If entanglement builds spacetime link by link, then every quantum connection we observe today, from lab experiments to distant quasars, isn't just a feature of the universe. It's the universe remembering how to be a universe, a cosmic habit it can't quite shake. And if that's true, the first entanglement wasn't an event. It was the first stitch in a tapestry still being woven, a reminder that reality might not be something we're in, but something we're all actively threading together. What if the reason quantum entanglement exists is simply because we're here to notice it? The anthropic principle, one of cosmology's most provocative ideas, suggests exactly that. It's the observation that the universe's fundamental constants and laws appear bizarrely fine-tuned for life, almost as if reality folded itself into just the right shape to allow observers like us to emerge. And if that's true, then entanglement might not be a random accident or even a necessary feature of physics. It could be a cosmic precondition, a prerequisite for a universe capable of asking questions about itself. Think of it like walking into a room where the thermostat is set to a perfect 70 degrees. You might wonder why this temperature until you realize the room was designed for human comfort. The anthropic principle applies that same logic to the cosmos. Of all possible universes with different physical laws, we find ourselves in one where entanglement exists because, well, we couldn't have appeared in a universe without it. Without those quantum links, atoms might never have formed stable molecules, stars might not have ignited, brains might not have evolved to ponder the mystery. In this view, entanglement isn't just a quirk, it's part of the universe's user manual, a line in the fine print that reads, must include quantum weirdness for life to function. But does this explanation hold scientific weight, or is it a philosophical shrug dressed up as insight? Critics argue the anthropic principle is a tautology, a fancy way of saying things are the way they are because we're here to see them that way. It doesn't predict new physics so much as retroactively justify what we already observe. If entanglement hadn't existed, we wouldn't be around to miss it, but that doesn't explain how or why it emerged in the first place. It's like saying rain falls because plants need water, true, but hardly a theory of meteorology. Supporters, however, counter with a compelling thought experiment. Imagine a hypothetical multiverse where every possible set of physical laws plays out in separate realities. In nearly all of them, the constants are wrong for life. Gravity too weak, electromagnetism too strong, quantum correlations too fragile. But in a vanishingly rare subset, the numbers align just right and observers blink into existence. From their perspective, their universe seems miraculously tailored, even if it's just the lucky winner of a cosmic lottery. If this is true, entanglement might not need a deeper explanation beyond statistical inevitability. It was simply the version that allowed the dice to roll in our favor. The debate gets even thornier when applied to entanglement's origins. Some versions of the anthropic principle suggest that consciousness itself might play a role in shaping quantum reality, an idea that veers into metaphysics. If observation collapses quantum probabilities into definite states, could the universe's first entanglement have been triggered by some primal act of attention? Or is that giving far too much credit to observers who arrived billions of years later? The line between profound insight and circular reasoning blurs fast, leaving physicists divided. Yet even skeptics admit the anthropic principle has its uses. By identifying which features of quantum mechanics are essential for life, like entanglement's role in chemical bonding or energy transfer, it helps narrow the search for deeper theories. Instead of asking, why does entanglement exist, we might ask, what's the minimal quantum architecture required for life to emerge? That shift in perspective could reveal hidden connections between entanglement and other cosmic puzzles, from dark matter's distribution to the universe's accelerating expansion. At its core, the anthropic principle forces us to confront the limits of explanation. Some questions might not have answers rooted in causality or mechanism. They might simply be facts of our peculiar cosmic address. Whether that's satisfying or unsettling depends on how comfortable you are with a universe that doesn't owe us clarity. One thing's certain: if entanglement is indeed part of life's fine print, it means the universe's first quantum link wasn't just a physical event, it was an invitation, written in the only language that could eventually produce someone to read it. After exploring 29 theories that weave entanglement into black holes, extra dimensions, and even cosmic simulations, we arrive at the simplest and perhaps most frustrating explanation of all: entanglement has no origin. It just is. No grand cosmic event, no hidden mechanism, no deeper structure. It's a brute fact of nature, as fundamental and unasked for as the speed of light or the charge of an electron. The ultimate null theory. At first glance, this feels like surrendering. After all, science thrives on digging deeper, peeling back layers until we hit bedrock. But what if entanglement is the bedrock? Some physicists argue that demanding an explanation for everything leads to an infinite regress, a cosmic why. With no end, you can't ask why the rules of chess are what they are. They're just the framework within which the game unfolds. Similarly, entanglement might be one of those rare, elemental features that define reality's playing field, not a piece moving across it. This perspective isn't just philosophical defeatism, it's rooted in empirical pragmatism. Think of gravity. Newton described its effects beautifully without knowing why masses attract. Centuries later, Einstein redefined it as spacetime curvature, but even that just pushes the question back. Why does matter bend spacetime? At some point, we hit a wall where, because that's how the universe works, becomes the only honest answer. Entanglement might live at that wall. Lab experiments confirm its effects with staggering precision, but no theory yet explains why particles sink instantaneously, only that they do with mathematical certainty. Yet the null theory grates against something deeply human, our hunger for narrative. We're storytellers by nature, wired to seek causes and origins. A universe where entanglement just exists feels like a book missing its first chapter, a tale that starts mid-sentence. This tension splits physicists into two camps. One embraces the null theory as a pragmatic endpoint, a sign that some mysteries resist unraveling. The other rebels, insisting that every phenomenon, no matter how fundamental, must trace back to something deeper. There's a third option, though, one that splits the difference. Maybe entanglement is a brute fact, but not an arbitrary one. Like pi's value or the golden ratio, it could be a mathematical inevitability, the only possible configuration that allows a stable universe to exist. In this light, the null theory isn't a dead end, it's a clue that we've stumbled onto a truth so essential, it doesn't need an explanation. It simply is the explanation. Whatever your stance, the null theory forces a humbling realization. Some answers might lie beyond the reach of why. And if that's true, entanglement's greatest lesson could be that the universe owes us nothing, not even reasons. It just is, and somehow that's enough. From the fiery crucible of the Big Bang to the whispering edges of parallel universes, we've journeyed through 30 radically different visions of how quantum entanglement might have woven itself into the fabric of reality. Some theories grounded it in physics, cosmic inflation stretching quantum links like taffy, or primordial black holes stitching spacetime with invisible threads. Others ventured into metaphysics, suggesting entanglement was the universe's first thought, a conscious act that collapsed possibility into existence. We've seen it as a shadow of higher dimensions, a relic of colliding brains, even a glitch in a cosmic simulation's code. Each lens offers its own revelation, entanglement as spacetime's operating system, as dark matter's hidden language, or as a cosmic free lunch balancing the universe's ledger to zero. What's astonishing isn't just the variety, it's how each theory reframes the question itself. Is entanglement a feature, a bug, or the very foundation of reality? The answer might depend on where you stand. If you love the elegance of symmetry, supersymmetry's hidden particle dances could feel irresistible. If you're drawn to the edges of computation, the digital physics angle might click. Or perhaps the raw, untamed creativity of the Boltzmann brain hypothesis sparks your imagination, or the quiet pragmatism of the null theory grounds you. That's the beauty of cosmology. The universe doesn't hand us answers, it invites us to play with possibilities. So here's my challenge to you. Look back through these 30 doors we've opened. Which one feels like it might lead somewhere true? Maybe it's the one that aligns with the math you trust, or the one that gives you that tingle of cosmic wonder. Drop your favorite in the comments, or better yet, tell us why you think we're all missing an even bigger picture. Because the wildest thing about entanglement isn't just that it defies explanation, it's that after centuries of science, we're still finding new ways to be stunned by it. If this kind of deep dive lights up your brain, hit that subscribe button. We're just getting started on peeling back the universe's greatest mysteries, from the quantum to the cosmic. Until next time, keep looking up, and remember, the weirdest truths are still out there, waiting to twist reality as we know it.